statistic, that HF statistic. It follows a chi-square distribution, and we'll get a p-value, a small p-value, and that tells us that we violated the independence of irrelevant alternatives. Let's see. Yeah. Now, given all that, the test sucks. It doesn't work 99% of the time, as we'll see, because we're going to test it on the Cracker data, and it's going to tell us that we're not violating things. Has poor sample size properties. It doesn't work very often. Even McFadden, well, even McFadden says it's really not a good test to use. You really just have to use common sense. Are these two things substitutes? Yes or no? Yeah. If they are, then we're violating IIA. We should use a model that doesn't assume IIA holds. It's that simple. We have these tests to test as faulty as they are because when you're publishing stuff, referees will often ask, have you tested for the independence of irrelevant alternatives assumption? So we have these tests. We have another test that is kind of similar. It's a likelihood ratio test, but it sucks equally badly. Essentially, we test at a formality. So how do we deal with the independence of irrelevant alternatives? We can combine these categories into similar, distinct categories. So in our situation where we had coffee, Gatorade, Coke, and Pepsi, we can combine Coke and Pepsi into soft drinks or carbonated drinks, which would be distinct from Gatorade and Coke. And again, we'd have to assume that these are all not substitutes. You can model these as a set of choices. First, whether or not to have coffee, Gatorade, or a carbonated drink. And then, once you've made that decision, we can choose between the two substitutes. This is called nested logit. And it's really cool. I'm sorry, it's very cool. It's really very cool. As we'll see in a minute, and we're going to take a look at this. Well, we'll just wait to take a look at it, because it's really cool. You can use a model that doesn't require the independence of irrelevant alternatives. Specifically, the multinomial probit model with alternative-specific data relaxes IIA, but it is extremely computationally intensive and very sensitive. It doesn't always work. So sometimes it won't find a solution. It'll run, it'll keep iterating, and at the end of however many beers it takes you to finally hit stop, or it'll just tell you, I can't find a solution. What's that?
So many beers.
Yeah, so many beers, yeah. Yeah, hopefully it's not too many. You'll give up after a while, or you'll pass out. One of the two. But we're going to see it fail also. So really a good solution is nested logit. We can use these mixed or random logit model, such as McFadden's choice model. And that actually allows us to, so the McFadden choice model is again another reason why I like that model. It does allow us to get around the independence of irrelevant alternatives assumption. All right, multinomial logit, some wacky model that doesn't work half the time. But it's a multinomial probit, but it has the probit interpretation and all that good stuff, so we're just going to burn through this stuff. All right, the nested logit model. I think this is going to be one of the more useful models coming up. Literally up until last week, specifically, I think it was Wednesday, up until last week, I hadn't heard of any of you guys, you being students, that had gone out into the workforce using the nested logit model until Wednesday. Someone told me that they were actually doing it because they told me they were actually doing it, which was awesome. It surprised me. But allows us to relax the IIA assumption. And essentially what we do is create these nests or clusters. Something like that. This is why it's cool. Remember when we talked about correlated errors and the variance and all that stuff, and we're violating all that stuff? But what it does is allows us to have correlated errors within the clusters. So these two can be substitutes. These two can be substitutes. These two can be substitutes. But we maintain the assumption that the errors are uncorrelated across the clusters. So correlated errors within the clusters, uncorrelated errors across the clusters. These are called level 1 decisions. Surprise, surprise, these are called level 2 decisions. And we can go to further levels. There is an implicit interpretation that level 1 decisions come first and then level 2 decisions. It's logically sound, but it's not mathematically required. We don't necessarily have to have the type A decision come before the alternative. So it's not structured in the mathematical properties of the model, although it's a logically sound assumption, and that's how we interpret these models anyways. Top choice called limb, and the branch and the twigs, all that kind of good stuff. So here's an example. You're deciding to purchase a car. All right, do you want to purchase a sports car, a luxury car, or a fuel-efficient car? So what the nested logit's going to do is assign probability to each of those. Now, once you've decided on a category, then you can choose among the alternatives. If I choose a sports car, what's the probability that I choose one of these? If I choose a luxury car, what's the probability that I choose one of these? And if I choose a fuel-efficient car, what's the probability that I choose one of these? Again, you're supposed to set these up so that, again, the substitutability between the products is within the nest, but across the nest, we're not going to have a substitutability problem. Hence, the errors are going to be uncorrelated. Again, I just kind of made this example up, but I've been told, and I know that the Teslas are pretty fast, and the new Tesla coming out, the sports coupe or something like that, is supposed to be insane fast. What's that?
Maybe if it comes out.
If it comes out, but they're saying it'll be the fastest production car in history, period.
They're saying something about the batteries that physically, the physics of it aren't possible. The batteries would be too big.
Yeah,
for the car. It was an interesting argument. I don't know.
Yeah, I saw the debut, and the quarter mile times were just they would beat Bugatti. So it's
instant torque. Electric motors.
Exactly.
Yeah.
So someone was telling me that you could conceivably think of a Tesla belonging in here. And that Teslas are actually kind of nice. It's not a cheap car either. It's 100 grand that I could probably go in here. So you've got to make a plausible argument. Again, I don't have data on this. I just made this up as an example. And already people were criticizing it. But you got to make a plausible argument. So if you're going to set these up if you're going to use a nested logit, you've got to set it up and make a plausible argument that, okay, we've got substitutes within the clusters, but not between the clusters. And these aren't definitive also. If you think Tesla belongs in a sports car, we can put it in there. If you think and run the results. If you think it belongs in luxury cars, we can put it in there. And instead of a Prius, we could put in some other fuel-efficient car. what is the Volt? Who makes the
Mr.
Volt?
Karma.
Who makes the Volt?
Chevy.
Chevy Volt? So we can put a Volt in there. And maybe Tesla belongs in a luxury car. So I think, again, I came up with this, so if I was looking at a sports car, I don't think I would be considering a Tesla, at least not the Model S. Perhaps a luxury car, again, they're not small cars, and they're not cheap cars. Like I said, they're about 100 grand, so it's about similar to what medium price luxury car would be. So I could see moving these around and changing these a bit. This is an example where we're going to look at using data. As you know, and as I probably mentioned, Stata is based in College Station, Texas, and these are restaurants in College Station, Texas. So this is data based on. What's that?
Makes sense now.
Makes sense now?
Where are these places?
I've been to all of these except for Mad Cows. That must have
That's
started.
fancy.
Yeah.
Yeah, I don't know.
Huh.
You gotta remember it's College Station, Texas. So.
Fair.
Okay. I know there were only 2 Freebirds, one in Santa Barbara, one in College Station, Texas. Mama's Pizza, they were better than pizza. Cafe and Shelley, you can go to all the time. Really good wings. Los Continuos, good Mexican food, and Christopher's was a kind of sit-down dinner. So okay, we're deciding to go to eat. We have to decide which kind of food to go to, fast food, family, or fancy, and then we have these substitutes within each nest or category. The data is going to be set up in long form. So remember that when you have alternative specific data, you have to have as many observations as you have alternatives. We have 7 different restaurants, so each decision, each ID, let's say, each person faces these 7 observations. So this is one person, this is another person, and each one of these people is going to have 7 different observations. We're going to have data in long form. Got 7 alternatives, 7 observations for each family. Cost, distance, and ratings are the alternative specific variables. And income and kids are the case specific variables. And again, the case specific variables don't vary across alternatives. So income is always 58,000, kids are always 3, right? Kids are always 1, income's always 39,000. It's the alternative specific variables that vary across alternatives because you can have different dinner specials. Let's say I go to, what's this dinner? Let's say I go to a different day of the week. Where there's different prices, different specials, student discounts, those kinds of things. So, all right. Defining the tree structure. We want to define that tree diagram. So we get something that looks like that. We'll see how to specify that. Where we've got the number of types each type was chosen, number of times each type was chosen, the number of observations, and this represents the number of families, and the number of times each alternative was chosen. Each family doesn't have to face all of the same alternatives, but they do have to maintain the same hierarchy. And this kind of goes back to that Tesla thing. We have to assume that all families agree that fast food is Freebirds and Mama's Pizza, family is Cafe Excel, Los Continuos, and Wings and More, and that fancier restaurants are going to include Christopher's and Mad Cows. So the hierarchy has to be assumed the same across all the families. All right, so here's output. Again, it's it's gonna be similar to a conditional logit in that we have our alternative specific variables. Again, the effect of the independent variable on the log odds of that alternative being selected relative to another one. So what does that mean? It means as the cost of one restaurant goes up, the probability of that one's gonna go down and the probability of the others is gonna go up. And as ratings goes up, the probability of choosing that restaurant is gonna go up, and the others are gonna go down. Yeah, so that's basically what we have there. And then we have our case-specific variables. And these are going to be within each of the three types: fast food, family, and fancy. Again, family in this case is our base category. And what these are going to tell us is, again, similar to our other ones, is that as income goes up, the probability of going to a fast food goes down relative to a family restaurant. And as income goes up for families, the probability of going to fancy goes up relative to family restaurants. We get something called a dissimilarity index. And these are these things here, yeah, dissimilarity patterns. Essentially, these are a test of the independence of irrelevant alternatives assumption. In other words, is our assumption of independence of irrelevant alternatives holding across categories? So here's a dissimilarity index for fast food, one for family restaurants, and one for fancy restaurants. And essentially, and then here's a likelihood ratio statistic that makes the assumption that all of these are equal to 1. So the null alternative is that all these are equal to 1. Our chi-square statistic for that test is 6. Our p-value is 0.07. We're kind of borderline here. In this case, we would reject at 10%, but not at 5%. So we're kind of on the borderline of whether we have violated our II assumption. Yeah. But let's see. Comparing models, we know how much I love the information criteria. These are garbage, but again, through by formality, we'll go ahead and use them. Again, I think that this is what firms are looking for. Specifically, firms are looking to, and this is a keyword that I hear over and over and over and over, firms are looking to map the path of consumers to different behaviors. So, for example, if you're on a website, ultimately you want to know what increases the probability of someone making a purchase on your website. So you've got, for example, 3 different pages you can go to. I can go to this page, I can go to that page, I can go to that page, and then from there I can go to another page. So which one of these is going to increase the probability that I actually buy that product? And here we can literally assign probabilities, right? So we can, I won't write on this. We can assign, this is going to be, we'll put probabilities up here, but here we can put 37, 57, 8, and so on. So we should be able to assign probabilities of for each of these outcomes. And these are nice because these are conditional probabilities. So this would say, given that you've already chosen to buy a sports car, I guess these would have to sum to 1. What's the probability that you choose M5 over a 911? And this would be, given that you've already chosen a luxury car, what's the probability you choose among these, and so on. So this is essentially what firms are looking for. How do we map the journey that people take to make the decisions that they end up making? And again, I can't tell you how many times I've heard people trying to figure out how to do this. Now, when I get asked to do this, or when I get asked about this, the first thing that goes into my head is nested logic. This is how you should do it. 99% of people out there have never heard of nested logic. As we'll see, it's just a command. We don't have to do the math. So it's pretty easy, but it answers the questions a lot of firms are looking for. So, and we're going to use it with Cracker Data also. All right, so let's take a look at it. We're going to look at a unfortunately, I don't have the case-specific data for the Cracker Data, but I do have a data set. What is this? Yes. I don't know how much you are into fishing, but here's a data set that has both case and alternative variables that I wanted to use. This is a relatively famous paper, semi-famous paper, about fishing choice. And the choices are, again, I don't fish, so don't ask me any specific questions outside of data. The choices of fishing are, I can fish off the beach, I can fish off the pier, I have a private boat, or I could rent a charter. And the variables we have are, well, let's look at the price variables. The price variables all start with P. Oops. All right. Not look up, I should look at the price. Yeah, so here's our price variables. And it's the price of beach fishing, the price of fishing off the pier, the price of having your own boat, and the price of hiring a charter. Then they have this Q variable, which is essentially the catch rate. How many fish you catch per hour, something along those lines. And there's a catch rate for the beach, catch rate for the pier, catch rate for a private boat, and a catch rate for charter. Those are going to be our prices and catch rate are going to be alternative specific because they're going to differ depending on time of day, where you go, and all those other things. So those are our two alternative specific variables. Our case specific variable is going to be, as it normally is, some sort of demographic characteristic like income. And again, if you think demographic, those are case-specific variables. They don't differ. My income doesn't differ depending on which alternative I choose. Whereas my prices and my catch rate are going to differ depending on which alternative I choose, because all of these people don't fish at the same time. This data is set up in what's called wide form, so that each row is a specific person fishing. So this first person chose a charter. That's the price they paid. That's the catch rate. Those are dummies for each beach, pier, private, and so on. This next person chose charter. This third person chose a private boat, or has a private boat, or has a friend with a private boat. Fourth person chose, so each row is a separate incidents of fishing. Now remember, when you have alternative specific data, this data has to be such that there's going to be as many observations for each individual as there are alternatives. So this one person is going to have 4 alternatives: charter, which they chose, and then private, pier, and beach, which they didn't choose. So this data set is going to increase by 4. So we've got 1,100 observations. We're going to have to change it. We're going to have to reshape it. But let's do what we did with the Cracker data. Let's see. Let's just look at a pie chart real quick. All right, so 38% chose charters, 35% private boat, 15 pier, and 11 beach. Yay for them. I've never understood the appeal of fishing. But I know people love fishing. I know.
Eat fish.
What's that?
You can eat fish, but
Yeah, I know people love they'll go at 5 o'clock in the morning to go fishing. It's insane. Let's look at prices. Yeah, obviously a charter is the most expensive, and then a private boat, and then beach and pier fishing are going to be relatively cheap. Mean prices, well, we just looked at median prices, or the interquartile range. This is not too interesting. This kind of tells us the same thing that we saw before. Charter was the most expensive, then private, then beach, and then pier. I don't know why I constantly fish off the beach, pier, but again, I don't know anything about fishing. I think this is more interesting in that it tells us the other prices when each mode is chosen. So, for example, this is the mean price of beach fishing when beach fishing is chosen, 35 bucks. It also tells us the mean price of fishing when pier was chosen, and when private was chosen, and when charter was chosen. Now, why it costs $137 to fish off the beach, I have no idea. I'd have to go back and read the paper. I was just looking for a data set. But what it does tell us is that when we fished off the beach, beach was one of the cheapest. And this is the mean price of fishing off the pier. And when we fished off the pier, pier is one of the cheapest. Even when we hired a private, or when we had a private boat, private, this is the mean price of private, was one of the cheapest relative to the other modes. And even when we hired a charter was one of the cheapest relative to the other modes of fishing. So essentially this tells us that people are following the laws of demand. So in the cases when they chose a charter, it was because a charter was cheaper. In the cases when they chose a private boat, it's because private was relatively cheaper, or at least one of the cheapest. So it's always good to observe people behaving rationally. All right, let's see. Yeah, here's our dummies. And I'm just showing that these are, in fact, dummies. Let's see. Shall I label everything? Sure. All right, so let's do what we did with Cracker data. We're going to use the multinomial logit model, knowing that technically it's wrong for 2 reasons. One, we have alternative specific data, and the multinomial logit model is for case specific data. And 2, we may be violating the independence of irrelevant alternatives if we view these as substitutes. So again, we can address those, but we can still run it. Doesn't mean we can't run it. So we run it, we get these results. Yeah, we run it, we get these results. Always check kind of the obvious things is, does the law of demand hold? So our first category, beach is our base category. Our first category is pier. That coefficient is negative, but it's not statistically significant. That should be, that should raise some questions. Our price of private is negative. Remember the cross price effect should be positive. The price of charter is positive, but it's not significant. The catch rates aren't significant. The only thing that seems to be significant is income. So kind of like with the Cracker data, we're getting mostly the right signs, but not always, but almost nothing significant. And we see similarly with private. Private, we see its own price is negative and it's significant, which is good. Cross price with peer is positive, which is good. Cross price with charter is positive, which is good. Yeah, so those are all good. Catch rate is negative. For private, it should be positive and it's negative, not significant. So again, we're not getting great results. Again, it could be that maybe these things don't matter that much. Or it could be that we're using the wrong methodology. So we know these are wrong. We're getting not real strong results. Case-specific variables, and we can do all that stuff. Technically, with case-specific data, we should only be using our case-specific variables, which is income. Again, this regression doesn't tell us much. Yeah, at least it's significant in 2 of those. Insignificant for charter, which you would think it would be. What we want to do is use the more correct methods. Specifically, we can, well, I guess we need to test for the independence. So we know that we have case as well as alternative specific variables, so we know we're not using the right tool there. We also know that the independence of irrelevant alternatives might be relevant, so to speak. This is a nice add-in for Stata. It's called mlogit test. Am I online? Yes. If you type find it, mlogit test in this data, it'll go find this add-in. It's like Outrigger. It'll take about a second to add in. But remember what the test, McFadden test is. There's 2 tests. There's the Hausman-McFadden test, and then there's the small